Hey guys, welcome back to day 27. Talk a redox review, and then we're going to balance oxidation reduction reactions. So let's talk about oxidation numbers. All right, in oxidation numbers, what are they? They're a way of keeping an account of electrons in chemical reactions. Now this does not necessarily reflect where the electrons are. It's how humans keep account of these electrons, how we do it, right? And it's a system that we use to predict behavior, because we like to predict behavior. So the common rules from Chem 1. First rule, element by itself is equal to 0. Elements by itself, if I have iron, if I have fluorine, oxygen, sulfur, copper, it doesn't matter. Those are all 0. Same number of protons as electrons. Second rule, monatomic ion equals the charge of the ion. So if I have Fe2 plus or Fe3 plus, O2 minus, Cu2 plus, these are my oxidation numbers. That's my oxidation state. 3, fluorine is -1 in compounds. Fluorine is -1 in compounds. The only time fluorine is not -1 in a compound would be when fluorine is an element by itself. So fluorine is -1. It's the most electronegative element. It's the biggest, baddest element, so to speak, in terms of taking electrons. Fluorine is going to be -1. Second biggest, baddest element would be oxygen. So 4, number 4, oxygen is -2 in compounds. Except, and I'll give you a couple examples. So oxygen difluoride would be 1, superoxide and peroxide will be 2 others. There's also another common one, the hydroxyl radical. I don't want to go get to though. So these are some exceptions where oxygen would be +2 there, -1/2, and -1. How can oxygen be -1/2? Well, let's look at that. If we draw the Lewis structure of O2- superoxide, we have 6 and 6, 12, 13 electrons. 2, 4, 6, 8, 10, 12, 14, 13. So we have a radical here. You have a radical, and that radical is going to go back and forth. So technically speaking, one of the oxygens has 2, 4, 6, 7 electrons. It's -1. The other oxygen is 2, 4, 6, 0. So one of the oxygens is -1. One of the oxygens is 0. But that goes back and forth, right? The radical's not going to stay on one oxygen. And so the average is 1/2, and that's good enough for our purposes of predicting behavior. Number 5. Now I'm going to skip to number 5. I'm going to say we're going to continue with the negatives. Chlorine, bromine, iodine are -1. in compounds, except when paired with fluorine or oxygen. So paired. This would be like ClO3 minus versus COCl2. So ClO3 minus is going to be plus 5 because it's paired with oxygen. Oxygen is going to become -2. Oxygen will be plus 5. Here, for COCl2, chlorine is -1 because carbon's there. Rule number 6. Hydrogen is +1 or -1. So hydrogen is +1 in compounds with non-metals. And it's usually written first or around carbon, So even in hydrogen acids, hydrogen is +1. It's -1 when paired with a metal, such as sodium hydride or calcium hydride. Then hydrogen's paired, it's written second, it's the anion. Okay. They exist, not usually water stable, but they exist. Most of the time hydrogen's +1. Now that's all hydrogen's going to be, right? Hydrogen cannot be +2. It's not physically possible for hydrogen to be +2 because hydrogen's 1 proton. So just note, right? Oh, I think hydrogen's +2. It's not physically possible. Right? And hydrogen's not going to get an electron configuration of lithium, right? And be -2. Being -1 is technically isoelectronic with helium, and that's okay, but we're not going to go to any more than that. So hydrogen's options are +1, -1, or 0. And last, group 1 is +1, and group 2 is +2 in compounds. Always. Kind of like the rules in my house. My children know that rule number 1, mom's always right. Rule number 2, when mom is wrong, see rule number 1. And that's how it is. So if you're doing what's the oxidation states here, and you see calcium is a group 2 metal. Oh, I wonder if calcium is a +1 or something else. No, calcium is +2 always. Well, it's not going to, calcium's +2. Something else is going to change. All right? Fluorine is always going to be -1. Calcium is always going to be +2. Those are our rules. Now, there will be a chance that you do not have fluorine, oxygen, or the rest of the halogens, hydrogen, or group 1 or group 2 metal. So then what do? We know that the oxidation number on an element in a molecule is the charge the atom would have if the electron were in the bond, were assigned to the more electronegative atom. So if you had, a nitrogen and a phosphorus, nitrogen's more electronegative. It's in the top 5 electronegativity. And if you don't remember electronegativity, that's a Chem 1 topic. Go to the book and look it up. But nitrogen would be negative, and the phosphorus would be positive. In this case, nitrogen would be -3, phosphorus would be plus. Let's define reduction and oxidation as well. So reduction, a lot of times I'll label it red. And reduction is the gain of electrons. A lot of times it's also the loss, well, it's also the gain of H and the loss of oxygen. It's the gain of hydrogen. So usually if I gain hydrogen, I'm going to be reduced, and if I lose oxygen, I will be reduced. Reduction, right, is, and we write it as something, let's use red again, something plus electrons going. Okay, electrons on the left-hand side of the arrow. Oxidation, ox is the loss of electrons, the loss of hydrogen, or the gaining of oxygen. And a lot of times for oxidation, we have X plus electrons. So the electrons are on the right-hand side of the arrow. So if you look at a number line here, if I drew a number line, 5, 4, 3, 2, 1, 0, -1, -2. So if I look at this number line here, if I start at 4 and I go down to 2, positive, I'm reduced. I'm reducing the charge. -1 and -2, I'm reduced. Oxidized, -2 to 0, that's oxidized. 1 to 3, that's oxidized. So oxidized, I'm becoming more positive. Reduced, I'm becoming more negative. Let's do some examples of this. All right, so now to remember, and I didn't say this yet, that the oxidation numbers add up to the charge. And what I'm going to have, I have compound X, Y, Z. My oxidation numbers are going to be up here. These are my ox numbers. Down here is going to be my math help. So we don't have to do it in our head. So for the first one, Fe, I have an element by itself. So it's 0. I have N2. I have an element by itself. It's also 0. HCl. Now we probably know what they should be, but let's just do the whole thing. They add up to 0 because there are no charge here for HCl. Well, if I go through my list, element by itself, no. Monatomic ion, no. Fluorine, no. Oxygen, no. The rest of the halogen, Cl, yes. Chlorine is -1. And so, now hydrogen also has a rule that it's +1 with nonmetals. And so this is going to work out beautifully. And we knew that before. Hopefully you knew that. Hopefully this is not new. A lot of this should not be really new. But hydrogen is +1 -1 for chlorine. SOCl2, we add up to 0 because there's no charge. Go through the rules. If I go through the rules, by itself, monatomic ion, fluorine, oxygen. Oxygen is -2. So I have a -2 there. Then I have chlorine. Chlorine is going to be -1 because I'm not paired with oxygen. There's another element there. And so that's a -2. So that means sulfur looks like it has to be +4. The reason I do the math help is 4 -2 -1 is not 0. But 4 -2 -2 is 0. So I like to do the blue math help But remember, these are the numbers we want. Permanganate. Now we add up to -1. I will start with oxygen, because oxygen is going to be -2. And that's 4 of them, so it's a -8. So manganese has to be 7. Ammonium phosphate. Okay. Well, what do we do here? We know they add up to 0. If I start, I got oxygen. Oxygen would be -2. And that's a -8 there underneath oxygen. And then if I keep going through the rules, I'll get the hydrogen is +1. And there are 4 of them. So that's and then 3. So 4 and 3, 12. Okay. Now I have N and P. And it might be confusing. I remember nitrogen is more electronegative, but I have 2 polyatomic ions. If I know my polyatomic ions, like we're supposed to, I have NH4+, and I have PO4 3-. Do you think the nitrogen's oxidation state with ammonium changes in ammonium phosphate? No, it doesn't. Or a phosphorus oxidation state, and phosphate is phosphate. It doesn't matter. It's phosphate. It's not changing. So we can, +1 here and -2, I can figure these out. So +1, -3. Let's do ammonia first. 1, that's +4, so that means nitrogen is -3, which is what it wants to be. And so if we would have came up here, nitrogen, if we would have put -3 there, that would have been a good choice. But we can always do the polyatomic ions separate. -8, so that's a +5. So plug it in, +5. Let's see, does this work out? -3 times 3 would be -9. 5 +5. Does this work out? -9 plus 12 would be 3. Plus 5 would be 8. -8 would be 0. It works. Excellent. So I can always do a polyatomic ion by itself because it's not changing. Okay. The next one. Last one of these examples. I have iron. I should be able to figure out what iron's oxidation state is in this. And if I look, what do I have? I have nitrate on the outside, 2 of them, and I have hydroxide right here. Water is neutral, 5 water, so it's overall neutral. So I have -1, 2 -1s, and a -1. So iron should be +3 here. Let's check. I have nitrate, so I can do nitrate by itself. NO3-. We start with oxygen's -2, and we know oxygen's going to be -2 in all of these. There's no fluorine. Hydrogen's also going to be +1, because with nonmetals. Okay. So -2 times 3 is -6. They add up to -1, so nitrogen has to be +5. And we think iron is +3. Does this work? Let's look to see if this works. Adds up to 0. So 2 times 3 is -6, times 2 -12. 5 times 2 is +10. 2 times 5 is -10. 2, 5, +10. +1, -2. Let's look. So we have right here, I have a -1. For the waters, I have 0. For nitrate, I have a -2. Works out. And so then we have a +3 here for iron, which it works. So that's oxidation numbers, and that's the oxidation states and how to do them and the rules. Next video, we'll look at balancing. Take care, guys.